Hello, today, everybody. Good Lord, I am not with it today. Welcome back, everybody. Today in calculus, we will be looking at what is known as improper integrals. And there are two types of these improper integrals. So we're going to spend two, sections on this one. So today, the first one we're going to look at is, what is known as the type 1 improper integral. And then the next session will be on type 2. Now, in terms of what's an improper integral, at least for the first type anyways, well, here, have you ever ran into a situation where you might be asked to find what is the area under the curve, let's say from -1 to infinity of 1 over x dx? Now, if you were to graph this out, you can see that over here, the graph would probably look something like the following. Normally in the, originally when we first introduced the idea of integral, the area under the curve, we don't consider what happens, or we kind of disregard or more like just never dealt with what happens when your graph is not continuous. So at x equals to 0 in this graph, you can see that it is undefined, so you cannot actually find the area under the curve. But that is not to say that it is not something that you can solve for, because if you look at it carefully enough, 1 over x is symmetric, and for the most part, you do have some parts that are going to, quote unquote, cancel each other out. So for example, let's say because we're going from -1 all the way to infinity over here, the area under the curve, if I were to kind of look at it, you can see how this part right here and this part right here all the way to 1, and let me just go ahead and kind of put the 1 over here. They net because the upper half and the lower half are the same. And so the result is that you technically should be able to find what is the area under the curve or get a numerical value, because this right here would then lead into the same thing as saying the integral from 1 to infinity of 1 over x dx. So these are examples of improper integrals, where basically your function is going to be undefined somewhere. And so maybe it's not continuous, or maybe you have a vertical asymptote, or maybe even just dealing with an integral where the boundaries are going to be positive or negative infinities. So the first type that we're going to be looking at, type 1, is what happens when you have an integral that has infinity in it, and how do you find what is the area under the curve. The second type of improper integral is what happens when you have a value that is not going to be continuous somewhere. How do you find the area under the curve then? So here is how we're going to kind of break each one then, okay? So let's go ahead and take a look for right now for type 1, okay? So we'll scroll down right here. So the first part, as we said, the improper integral is what happens when you have a boundary that is either positive or negative infinity. So in the first case, we say that if you have an integral from some value of a to t of f of x, and those values are always going to exist, meaning that you can find the area under the curve, where t is a value that's greater than a, then we can say the following, that the integral from a to infinity of f of x dx can be rewritten as a limit as t approaches towards infinity of the integral from a to t f of t dt. So here, let me just kind of draw this out over here on the right hand side. So that means that let's say that we have a left bound which is going to be somewhere at a. And then on the right, what's going to happen is you're going to have some value t where you're going to find the area under the curve. Now, this theorem or definition says that if your area under the curve is always going to be finite, meaning that you can always find the area under the curve, right? Then what we can do is, if we have to find the area under the curve going to infinity, we can write this as a limit then for this problem, and then hopefully be able to solve for it. So that's, hopefully kind of a straightforward idea behind it. We'll look at some problems in just a little bit as to how to apply for it. For the second part, it says if you're going to the left to negative infinity, is the same thing. So that is to say that if the integral from t to a of f of t, x dx is going to be defined or exist for all values of t that is less than or equal to a, then you can write the following then. if you're trying to find the area under the curve from negative infinity to a of f of t dx, then we can write that as a limit problem, and then take the integral of t to a of f of x dx. Basically, in short, what this means is if you ever run into an integral where there is a infinity or negative infinity, we replace those negative infinity or infinity with a limit problem, and then be able to solve for it using the old school way of doing it in the first semester. So here are some of the terminologies that we're going to be using here. The first one is that at any time that you can find the area under the curve from some number to infinity or negative infinity, we say that that is going to be convergent. So meaning that if you find the area under the curve, you take the antiderivative or whatever it means, and you get a finite number, like say 4 or 5 or negative 20, some sort of real number, then we consider that as convergent. But whereas if you cannot find a numerical value for the area under the curve that deals with infinity or negative infinity, we call that divergent then. So those are the two terminologies that we have. Convergent and divergent, they should sound familiar because you've dealt with them back in Algebra 2. Converging means that it adds up to some sort of finite value, but whereas divergent means that it does not add up to some sort of finite value. And finally, for the last part, and this one is kind of important for some of the problems in the future. Let's say that both of the area under the curve from a to infinity of f of x dx and also from negative infinity to a of f of x dx are convergent. So let's say that you can actually find some numerical value for the left and also for the right. Then what that means is you can use this as a replacement. The area under the curve from negative infinity to positive infinity can be broken down into negative infinity to a of f of x dx plus from a to infinity of f of x dx then. Okay, so meaning that you can actually break it into two parts. So then now we can go ahead and apply the limits then. All right, so let's go ahead and see some of these problems and see how it works out for all of these, okay? So for these problems right here, what I want to do is determine if each of the integral is going to be convergent or divergent. So simply what that means is find the area under the curve. And if it exists, then it's convergent. But if it does not exist, then it's going to be divergent. So here in the first one, I want to solve for what is the area under the curve from 5 to infinity of 1 over x dx, just something basic to begin with. So as soon as I see the infinity in the integral, then that's where this improper integral thing comes in, because we don't like having an integral that is going to be involving infinity. That's why it's called improper integral. So what we'll do is we'll go ahead and rewrite it. Limit as t approaches towards infinity from 5 to t of 1 over x dx. Okay, so changing the improper integral into a limit problem, and hopefully we can solve for that. So now we'll go ahead and go through the procedure as we would normally. Limit as t approaches towards infinity, and we're going to take the antiderivative. So ln of x, absolute value, and then the boundary from 5 to t. Now we're going to go ahead and apply the upper and lower bounds. So limit as t approaches towards infinity of ln of t, absolute value, and then minus ln of absolute value of I. 5, not I, okay? And so this limit problem hopefully should not be something that is difficult for you to be able to solve for. So for the first part, you can see that this is going to be infinity then as a result, because ln of anything that is going to infinity is going to be infinity, minus 5, ln of 5 actually. So let me go ahead and replace that. So minus ln of 5. And so because this is not a numerical value or a real number, so then that means that this is going to be divergent then. Okay. All right. So that's going to be our first one. Now for the second one, same deal. Let's say this time I want to find the area under the curve from negative infinity to, and let me change that a little bit because we're kind of stepping into the boundary of type 2 and I don't want to deal with that. Let's say the negative infinity to negative 2 for 1 over x cubed dx. So here, same idea. We first notice or recognize that you have a boundary that deals with some sort of infinity. So that is the improper integral. We'll go ahead and do a replacement then. So limit as t approaches towards negative infinity, and then the integral from a to negative 2 of 1 over x cubed dx. So same as before, we're going to go ahead and solve for the antiderivative first. So limit as t approaches towards negative infinity. The antiderivative in this case is going to be negative 1 over x squared, and then there is going to be, if I'm correct, there's going to be a 2 on the bottom because of the reverse power rule. And your boundary are going to be from a to negative 2. Okay, go ahead and plug in the each one. So we now have a limit as t approaches towards negative infinity. The negative 1/2, I think I'm going to go ahead and take outside. So then that way we can, not worry about that. So the upper bound in this case, if we plug it in, that's going to be 1 over 4 because it's 1 over negative 2 quantity squared. And then minus for the other part is going to be 1 over a squared. And for each one of those, we're going to go ahead and drive t to negative infinity. So the result is that you will have the negative 1/2 from the outside. We also still have the 1/4 and 1 over a squared as t approaches towards infinity. Oh, sorry. All of a sudden, I just changed it to a. So that is my fault. I don't know where that a actually comes from. So these are actually supposed to be t's in this case because, well, my variable is a t. I even wrote it there and I wrote something else. Okay. So there it is. Then the last part, if I were to plug that in as t approaches towards negative infinity, you're going to get zeros then. So then this is going to be equal to negative 1/8. And so because this is a finite value, a real number, then that means that we can say this is going to be convergent then. Okay. All right. So hopefully that doesn't look too bad. Now, here's a side question for you that you should consider for future references. For what values of p does the integral from 1 to infinity of 1 over x to the p dx converges? Okay, so looking at these two examples that I did over here, when is this going to converge for what values of p? So, something to kind of chew on for the time being. All right, let's look at a couple more problems, and then that'll be it for right now. The next one right here, this is going to be the same idea right here. We have an improper integral because we have infinity and also negative infinity in the integral. Now, this is where you actually have to be careful. As much as it seems like it's convenient to do the following, you actually cannot. And here's what I mean. A lot of times we might think, okay, well, what if I wrote it as limit as t approaches towards infinity, and then I'm going to make it from negative t to positive t of 1 over 1 plus x squared dx. Believe it or not, this actually does not solve for the problem, and it's the wrong way of doing it. So actually, you cannot make it so that it's one single variable to represent both positive and negative infinity. So that is actually out of the question. So instead, we're going to have to use the rule of breaking it into two parts, which we did over here and which we did over here. Okay, so we're going to go ahead and take this and break it into two integrals then. So the integrals that I'm looking at are the following. What's an easy value to use for somewhere in between? Doesn't really matter where, but I think 0 is probably the easiest. Okay, so here's what I'm going to write. I'm going to write the following then. Limit as t approaches towards negative infinity of the integral from t to 0 of 1 over 1 plus x squared dx. And then we're going to say plus limit as, let's use a different variable in this case. Let's say that as u approaches towards infinity of the integral from 0 to u of 1 over 1 plus x squared dx. So notice that I broke it into two parts, as we said, because we want to be able to use that definition from earlier, where one of the boundaries, upper bound or lower bound, has to be some sort of numerical finite value that's in an interval. Okay, so now we're going to go ahead and solve for each one. Okay, limit as t approaches towards negative infinity. The first one, well, that is just going to be, let's see, tan inverse, if I remember correctly, right? So that's going to be the tan inverse of x, and then the boundary from t to 0. And then plus for the other part, limit as u approaches towards infinity. And then that is going to be tangent as well. So tan inverse, actually, from 0 to u. Now let's go ahead and solve for each part by plugging in. limit as t approaches towards negative infinity. So we got tangent inverse of 0 and then minus the tangent inverse of t. So that's the first piece. And then we're going to say plus, and let me use a different color just to make it a little bit easier to see. Limit as u approaches towards infinity, the tan inverse of u, and then we have minus the tan inverse of 0. Okay, so that's going to be the other part. All right, let's go ahead and solve for each one individually then, okay? In the first piece over here, tan inverse of 0, well, that is equal to 0, so that's easy enough. And then minus, for the other part, limit as x approaches towards, as t approaches towards negative infinity, tan inverse. Well, where tan inverse, what happens when tan inverse goes to negative infinity? That is going to go to negative pi over 2, because if you recall correctly, right, the tan inverse graph looks something like this. So y is equal to tan inverse of x. We're over here, that is going to be pi over 2, and we're over here, that's going to be negative pi over 2. So that's where this negative pi over 2 thing comes in, okay? And then plus, for the other side, limit, well, actually, let's get rid of the limit part because we're applying it now. The first part of it, that is going to go towards positive pi over 2. And then the last part, that's going to be equal to 0. So now looking at what we have, we can see that the pi over 2 are going to be added together, and the answer is equal to pi, so therefore this is going to be convergent. All right, so there it goes. All right, now let's go ahead and look at this last scenario over here, which hopefully, doesn't look too bad because we're not breaking into two parts anymore. But this one, there is a unique aspect to it, and that's why I want to mention it. So the integral from 0 to infinity of t times e to the negative t dt. Okay, so first we'll go ahead and go by our regular rule, which is going to be apply the limit. So limit as t approaches towards infinity of 0 to t of, oh, actually I'm using t already, so we can't use that variable. Let me go ahead and change that, okay? So not t over here, not t over here, but let's just go ahead and say a for right now, okay? So a, and then we have t e to the negative t dt. Now, for this problem right here, we have to use integration by parts. So here I'm going to go ahead and solve for on the side. U is equal to, let's see, something. dv is equal to something. U is going to be something that diminishes, so that's going to be t. And then dv is going to be the other thing that I'm going to take the antiderivative. So v is equal to negative e to the negative t. U is equal to dt in this case, okay? So this now turns into the following then. Limit as a approaches towards infinity. Let's see, the first part is going to be negative t e to the negative t, and then we have plus the integral of t e to the negative t dt. Okay, so hopefully I did everything correctly there. And we'll deal with the boundaries in a little bit. Let's see, it's supposed to be from a to 0. 0 to a. We're going to finish the integration part first, okay? So limit as a approaches towards infinity. So negative t, e to the negative t. And then the next part will be minus e to the negative t. And now let's go ahead and apply the boundaries in this case then, okay? So let's see, limit as a approaches towards infinity. The first part will be a substituting for t. So that's going to be negative a multiplied by e to the negative a, and then minus e to the negative a. And then we also have, for the other one, which is going to be plug in the lower bound. So minus, for the lower bound, if we plug it in, looks like you're going to get 0, and then looks like it's going to be minus 1, okay? So that, hopefully, the lower bound was the easy part. Now, we're going to have to apply the limits in this case. And this is where it goes back a little bit to the first semester. So in the first one, limit as a approaches towards infinity of negative a multiplied by e to the negative a. The second part, that one is not too bad because, well, we've seen where this is, what this is. As e approaches towards negative infinity, that's going to give me 0. So we can go ahead and make a substitution for that. So that's going to be minus 0 minus plus 1 in this case. So the problem, the factor, the x factor in this case is going to be this guy. Well, this is where, let's see, if you remember, L'Hopital's rule is actually going to come in. And let me write it in that form so you can see it. Limit as a approaches towards infinity. And then we have negative a divided by e to the a, because that's how we can rewrite it so you can see L'Hopital's rule. And then we have the plus 1 on the side. You can see the top part right here, limit as a approaches towards infinity for negative a is going to be equal to negative infinity. And then for the bottom part over here, limit as a approaches towards infinity of e to the a is also going to be infinity. So this right here is what is known as the indeterminate form. Okay, so indeterminate form, net form. So that's where we have to use L'Hopital's rule. Okay. So that means we have to take the derivative of the top divided by the derivative of the bottom. So let's see, that's limit as a approaches towards infinity of negative 1 divided by e to the a. And then we have the plus 1. The 1 part, don't worry because that's independent of the L'Hopital's rule over here. L'Hopital's rule is only looking at this piece over here, okay? All right, so now we can go ahead and solve for this. As a approaches towards infinity, then that means that that is going to go to 0 because the denominator is getting bigger while the numerator stays the same. And then plus the 1 that we have on the outside, so therefore it's equal to 1. So this problem means that it's going to be convergent then, okay? All right, thank you so much for watching. We'll come back next time for part 2 then. I'll see you later. Bye-bye.